June 8, 2023. Where we left off, I was discussing about the Dirichlet function and the checkerboard function, and the idea being that the Dirichlet function is on or off at rationals or irrationals respectively, or vice versa. And then in terms of its measure, it's basically the rationals have measure 0 in the standard theory. And the idea was to make it similarly so as for the continual limit of a checkerboard function that's measure 1/2 over any sufficiently long region, terms divided by the length of the region, or any even length region in integers. And so that makes y that there's the signal continuity to consider with respect to density 1/2 and the Dirichlet function, which is a very regular sort of example of an analytic system within otherwise a system with analytical character that's well defined and has measure. It's measurable. That's yet arises in a bunch of places in physics, like for example in our talks about the path integral. And here is after the Dirichlet kernel and these kinds of things about the definitions of analysis of Riemann and Lebesgue and Sorites, and with regards to others and these kinds of things. And then we got to talking about the uniqueness of such functions and where they exist, of why it's possible or not to imagine that two Fourier series with the same limit are the same functions, Fourier series, when as with regards to where they aren't, it would be some pretty contrived reason why the bounds of limits are so sorted out that it makes for signal continuity or field continuity, the central standard milieu for all things analysis in the coordinate and Cartesian and up from the inventors of the calculus, the discoverers of this calculi. That then we got up into a section talking about Cantor and Cantor's exploration and his assertion that it was so, that it's unique, vis-a-vis that it's not. And that's just an example of kind of thing about that it basically is so where a given topology is fixed as the only topology. Kind of like where there's other things like so. By neighborhood of P, Cantor meant an open interval containing P. And so can there be anything different about a neighborhood than an open interval about that with regards to the neighborhood of it, or what was the topology? Because topology just kind of defines neighborhoods, and it's for continuity's sake almost completely, and it's about the completeness of the same, and that the limit points or critical points exist everywhere and these kinds of things. They need to define the derived set P prime of P as a set of all limit points of P, which is, if P is continuous, it's P itself. The second derived set, P prime prime of P, as a derived set of P prime and dot dot, till after n iterations, the nth derived set of P is the derived set, P n minus 1. Later, he would refer to a set P whose nth derived set is empty for some n as a set of the first species, all other sets being in the second species. So one reason to consider that is in terms of the density about these points. It's an aspect of the vanishing of the topology and this kind of thing, and what order it would result that this rank reduction would make it so that it ends up being 0 when prior to that it's non-zero. And then that's similar to the considerations here about the operator calculus and the otherwise the working up of index formulas and addition formulas and such things that make for integer ordering and ranks, and what result things that come down from C empty, the class of infinitely differentiable functions, down to where they goes to that for polynomials that they go to 0, and that for various other functions like the sinusoidal functions and so on, that they come down, and that for the exponential functions that they stay the same, and these kinds of things. That these are some of the ongoings that here it says about, a matter of fact, is how dense something was and how sparse it went. Later, he would refer to a set P whose nth derived set is empty for some set n as a set of the first species, all other sets being of the second species. that then gets into the interval that's not having any points in it that is somehow only defined as being an interval is called the degenerate interval. So when we talk about the deconstructivist accounts and the quasi and the pseudo and the degenerate, and here with respect to what is a neighborhood and when it becomes, according to what's called the heap paradox or the Sorites paradox, that according to Sorites, S-O-R-I-T-E-S, Sorites, what happens is that there's a grain of sand. And at some point in time, if you have enough grains of sand, it makes a heap of sand. And so when did it become just a count of grains to a heap of sand? And what that reflects is what's called the transfer principle, which is what is so for each is so for all. And so when you can make heaps out of the heap of sand and they're still heaps, then it's kind of what's so for some is so for all. And when it's not, then it's like each of the grains of sand themselves, the utterly elementary, the individual of a continuum of a heap of sand, become these individual of the continuum of the heap of sand. And that when it's a heap is effectively infinitely many grains of sand, or it acts as like a fluid and aggregate itself is sand, kind of like when you talked before about the sand painting in the between the plates of glass and the oil in the field, so that you could turn it upside down. It's like a sand hourglass and use it as a piece of timekeeping. Here it's what's going on with these points is similar, and it's not really said how it goes from one to the other, it just kind of says that it does go from one to the other. And these days there's various reflections on that in the standard. When they talk about the hyperreals, then the idea is that, well, we just have a halo of points in a neighborhood around each point, and it's separated from otherwise any interval or whatever defined by real valued endpoints according to the standard reals, and it's what's called a conservative extension or equity interpretable with a conservative extension of the standard. So it's not really saying anything at all. It's just a manner of speaking, saying that according to the analysis, for something to get from the finite to zero and in a continuous action of a sort, it has to go through all the infinitesimals to get there. The non-standard analysis then makes for these infinitesimals as like standard infinitesimals, which is kind of like Peano's infinitesimals. And so Peano, when I studied people who have their infinitesimals, has that. I think Aristotle's continuum is probably closest to most people's idea of standard infinitesimals. There's an infinitude of them. They're constant, monotonic, strictly increasing, and they're constant. The difference between them is constant. They're monotone. They only increase, and they're strictly increasing. The monotone being either increasing or decreasing. So they're constant, strictly increasing. And that these are pretty familiar to people, and so pianos are pretty close to that, except they're kind of like coming from the outside. So they're kind of more like as of a doubling space where they live. And then sort of Vitali is like when Vitali said, "Look, I can take a unit interval and I can split it out from all the limit of these ratios, these polynomials, and show a set." Then what happened was the rest of the world at the time said, "Oh, you've established their non-measurable sets." But what he'd really built was a doubling space according to infinitesimals, and how standard infinitesimals, when you actually, that only exist in their line. They only exist as parts of a whole. They only exist as line elements or path elements. The function that defines them, if you change that, then they basically, the properties that establish them as elements of a range of a function vanish. So then when Vitali was able to show that he could split it up into all the different pieces and found it doubles, that's basically what happens for this equivalency function, or what, because if you kind of chart the points on line and make it for the range, and you take it, and so you decide to integrate that, instead of looking like the identity dimension from 0 to 1, I'll just split out into infinitely many pieces, kind of like this checkerboard that was just kind of shrunk in from a whole line and fit into 0, 1 to make for a Dirichlet function with measurable analytical character in a specific value 1/2, take the integral of the natural unit equivalency function, or n over d, as n goes to d, as d goes to infinity, the continuum limit of this function in integers, is pretty simply interesting that its integral is 1 or twice what it would be, according to that it's just n over d is looks like the identity dimension, as in x over y, x goes to y goes to infinity. So, and then with regards to the uncountable, of course, has that you can't have the real numbers be an Aristotle's continuum, because then it would be a function between the naturals and the reals, which would be according to Cantor's Schroeder-Bernstein theorem, that between two sets that have a bijection between them and thus share the same transfinite cardinal, there would be one between those in the power set of integers, which would be proven not to exist by the theories of uncountability. Well, instead, it's a special kind of function because it's not a Cartesian function. So Cantor's uncountability results are restated. There are no Cartesian functions between a set and its power set. And there exist non-Cartesian functions, in particular this one kind of unique example. And then when you get talking about unique, it becomes really unique and really central. It's an Aristotle's continuum redone for 21st century. Cantor's 1872 paper on trigonometric series is concerned with sets of the first species exclusively. He proved the existence of sets of the first species by starting with an arbitrary number and using the axiom stated above. Given a set of points P, if there are an infinite number of points of P in every neighborhood, no matter how small of a point P, then P is said to be a limit point in the set P. He proved the existence of sets of the first species by starting the arbitrary number and using the axiom stated, identifying it with a point P on the real line. Then he took P to the n equals the set containing P and worked backward from there. Using his newly constructed theory of the real numbers, he then considered the points corresponding to a sequence of rational numbers determining P as elements of P to the n-1 with a sequence of rationals determining each point of P to the n-1 and so on. The set of points corresponding to all these rationals is of the first species. On this basis, he proved his most general uniqueness theorem, that if the Fourier series is equal to 0, holds for all values of x in negative pi except for those corresponding to a subset of the first species, then a naught equals 0 and a sub n equals b sub n equals 0 for all n greater than or equal to 1. So he's established that there's this trivial sort of case, and what it makes for is basically just the center of that. And then there's a consideration as to why that's really a result or product of not so much the topology, but and as a matter of fact that that something like the Dirichlet function does not have a corresponding example with measurable character, because such a thing doesn't exist in Cantor's real numbers. Cantor's real numbers are very closely associated with the equivalence classes of sequences that are Cauchy. If there's any definition of real numbers, it's that there exists the integers, then the ordered field, the rationals, or model thereof, then the complete ordered field, which is the equivalence classes of the sequences that have the Cauchy property, and that's given by axiomatizing for the ordered field, the rationals, that there's the least upper bound property satisfied for some object called the complete upper ordered field. And so to say that this is kind of like a trivial singularity for our deconstructive account, as we're talking about singularity theory and the multiplicity theory, so exposed in the dual complements and the dialectic, that it's a thing, and as to why that's so. Another curious fact, and people are usually exposed to, is the uniqueness of the complete ordered field up to isomorphism with the complex numbers. But it's so that you can take a continuum limit of field operations, which basically make for squeezing a field into -1 to 1. And so, and as regards to whether that's isomorphic to the field is not really the same. You'd have to say it's according to a geometry, which is where something like Lobachevsky geometry or Ramon's geometry or these other non-Euclidean geometries that also have interesting conformal mapping properties to be able to draw a projection of one space into another space and preserve in neighborhoods, i.e. in an arbitrarily small region, what would be the affine conformal mapping. This is not exactly the same thing, and so it's its own little geometry in that kind of world. Of course, when you hear non-Euclidean geometry, it doesn't mean an absence of form and proportion. It means something sensible, functional, and tractable about that. There's a conformal mapping to it, and you can form results on it, and then you can get back to it, the Euclidean geometry, and make sense, and that it's fungible and tractable again. So when that's said, and there are like multiple points at infinity as a matter of perspective or anything like that, that's again not really. It's important that that doesn't be seen as arbitrary mathematical constructs that are free of any structure. They're still all part of the same universe of all the objects. Now that's a little broad, of course, because when I say universe of all the mathematical objects, it's only those things that really exist, compared to the universe of our theoretical objects, which can include any conjecture in words, or even the conjecture of things absent from them. The world of theory is the only place where parallel universes can live and exist. In the real world of mathematical objects, there's a universe, and it's complete, and we're in it. It is a theory, which suffices by itself. So with regards then to this context about the Cantor's famous work in trigonometric series to prove the uniqueness of the Fourier series, as you can infer from my opinion about it, is that there's some questions about it that are reopened because the assumptions changed, and it was found there was more to it than what was present at the time. Having found his motivation on questions about trigonometric series, Cantor had just laid the foundations on which he would then build his acclaimed and controversial theory of sets. He defined many of the concepts familiar to anyone acquainted with mathematical analysis. Here's an example. An infinite set is one that can be put into one-to-one correspondence with a subset of itself. A closed set is one that contains all its limit points. That's like the least upper bound property and this and that. The set is open if each of its points is the center of an interval contained in the set. I don't know about that. A set is open if it doesn't contain all its limit points. A set is countable if it can be put in a one-to-one correspondence with the positive integers, and many more. He introduced the concepts of union and intersection of sets. Of course, union and intersection are natural operations that sets just have. And proved that the set of rational numbers is countable and the set of real numbers is not. According to that, uncountable here means there exists no Cartesian functions between the integers and the power set of the integers. And then as according to Cantor, Schroeder, Bernstein in Cartesian functions. But his main work on set theory and transfinite numbers was yet to begin and would be developed in a series of papers in the Mathematische Annalen beginning in 1879, including with two major works of 1895 and 1897 that the interested reader can consult in an edited English translation. And it's Jourdain's. Jourdain has a translation, and I've read this, and sorry. This is then the way it was. In 1870, Cantor gave the first steps toward the theory of sets by investigating a set of points at which Fourier series is 0 may fail to hold and still imply that A sub n equals B sub n equals 0. This is instead the way it could have been. In 1870, Hermann Hankel could have given the first steps toward the theory of sets when he investigated a set of points at which a function may be discontinuous and still Riemann integrable, but it was not to be. And in fact, his premature death prevented him from even becoming acquainted with Cantor's greatest achievements. About the life of Hankel, a student of Riemann, seeking the necessary and sufficient condition for integrability. Here, that's usually framed these days in terms of measure theory and the measure theoretic. If it has analytical character and a well-defined measure according to measure theory, you can integrate it according to its sigma algebras, taking their unions. That's the current usual working definition, and it's pretty applicable because it basically makes for that area is a conserved quantity when in the non-deformable in the affine. So he's talking about Hankel. And I think Hankel is famous for some kinds of transforms because when you come to some other ones, there's Hankel and Millen in this. If this is the same Hankel. True, Riemann had already given such a condition, but in view of his example of a highly discontinuous integrable function, Hankel wanted to characterize integrability in terms of the set of points at which a function is discontinuous and started by defining the jump of f at point x naught to be the largest of all positive numbers sigma such that in any interval containing x naught, there's an x for which the absolute value of fx minus fx naught is greater than sigma. This is kind of like the intermediate value theorem or the mean value theorem. Then if Fourier sigma denotes the set of points at which the jump of f is greater than sigma, big S of sigma, Hankel came to the conclusion that a bounded function is integrable if and only if, for every sigma greater than 0, the set S sigma can be enclosed in a finite collection of intervals of arbitrarily small total length, that there's a covering of sort of it. When a set can be so enclosed, we shall say that it has content 0, and otherwise it has positive content. So when he says content, he means analytical characters, content, measure, that which is integrable, that which is measurable. Therefore, a bounded function is integrable if and only if, for every sigma greater than 0, the set S sigma has content 0. But instead of developing these ideas, Hankel next made a mistake and stated the wrong theorem. First, he defined the set to be nowhere dense. This is modern terminology due to Cantor. If between any two of its points there's an entire interval, it contains no points of that set. Well, here it's nowhere dense if there's any set that's it's nowhere dense in the set that's the rails as a point set if the complement of that set is I'm sorry, I was thinking continuous. I was going to explain how nowhere continuous but dense, but nowhere continuous. But here, nowhere dense is sparse, and that there's modern terminology. As between any two of its points, there's an entire interval that contains no points to the set. And then, erroneously thinking that a set has content 0 if and only if it is nowhere dense, kind of is, but he stated that a bounded function is integrable if and only if for every sigma greater than 0 the set S some sigma is nowhere dense. So when I say kind of is, I mean in the standard. That otherwise we get into these things going on like line continuity, field continuity, and signal continuity. Half of the statement is true, for it is quite clear that if S sigma has content 0, then it is nowhere dense. But the converse is not true, although it is widely believed in large segments of the mathematical community for more than a decade. However, Henry John Stephen Smith, civilian professor of geometry at Oxford, carefully read Hankel's paper and found the error. Furthermore, in a largely ignored paper on the integration of discontinuous functions of 1875, he used several methods to construct no or dense sets of positive content. The interesting thing is that it is easy to exhibit functions discontinuous on such sets that are not Riemann integrable. Well, this gets into quite a thing here. In this descriptive differential dynamics, what we have is this descriptive differential dynamics are all about continuum mechanics and continuum dynamics. And so that what's the differential in the integral versus like, well, for lots of functions that are not themselves differential equations defined by their own differential, it's really simple. And then we get into differential equations where they have dynamics about the functions and their recursivity and their reflections on their stuff. And what that needs to have for completions and closures and convergence, that it works out that it has well-defined analytical character and measure and integrability and differentiability. And then we get into here are these kinds of examples about the integrability and the definition of the integral and what it means for a domain to be continuous. And well, the standard, at this point in time, the standard curriculum has kind of been squeezed down to one, and the field continuity, and so when you get into Jordan measure, which has the line elements and looks like Aristotle's continuum, and it makes for that, this and that, but you can't have sigma algebras because this whole uncountability bit. And similarly for the signal continuity, it's like, well, nobody has that their half like a checkerboard function because it's all lost in Cantor dust. Because the basically the very, very fundament has the functions are Cartesian. That now what we'll do is and now I think of René Descartes, it's generously and fondly because Grandpa was a poet of two in a sense, and so they're cousins. That it's still something that people have thought that it always exists, and it kind of always does, but there's this existence of a non-Cartesian function that's so proved to result and be this counterexample that bridges the gap, as it were, and how it bridges the gap, then that it's gaps between it and its definitions and others of the descriptive dynamics of continuous domains has to be bridged up. In fact, quite a number of these functions can be exhibited, but they are all sufficiently weird, and their mere existence does not detract from the wide generality and applicability of the Riemann integral. See here, for example, you can build for the line continuity a intermediate value theorem, and so you can kind of define a suitable integral for that also happens to model in small pieces the Riemann integral. Besides, it also has its own special character and other effects. And then it's similar for these ideas of these other geometries that are useful. They're not weird. They're simply reflections that come back and forth. They're the utterly non-sensible, non-fungible, and non-tractable has that's basically disallowed from mathematics because it's not mathematics. While at the same time, anything that can does exist. And when we think back to reading from Halm, on this very notion that he as a historian and a student of philosophy, which all researchers and foundations are, he rejected strongly this idea of continuity as an overarching principle, and said there's got to be at least this discontinuity between our reality and the Platonic universe of things. And it's fair, but at the same time, you can also reflect upon that you don't need a discontinuity from the Platonic universe to still have free will, or even just whether or not that having free will or not is or isn't perceptual and phenomenological itself. It still is, and it would be in effect, as it were, if it was. So, in this sense, one need not reject strong mathematical Platonism and mathematical universe hypothesis as long as it's figured out that there are completions of that it would also require kind of a complete and consistent theory. So there's some revisiting how Goedel did mathematics this wonderful favor, mathematics and mathematical logic. Goedel establishes incompleteness theorems when they're studying the theory and this universe and all this stuff put together after set theory was put in stone, and that its axiomatic descriptive set theory ended up being a great suitable model for all kinds of standard real analysis and thusly most of the rest of mathematics, and then for things like these other functions, that they were just made untractable or unfungible or unsensible in a sense, that they were excluded and restricted. The Gödel left the door open for that there's something outside those theories, because he proved the thing about the objects of the theory that you can look at one of two ways. One is that the theory is neither a consistent and complete. It can't be both consistent and complete and strong enough to model all integer arithmetic, so that there would always be conjectures and theorems inaccessible to this whole thing. But another way to look at it is it just makes it there's extraordinary objects outside the results of the theory. So even though the theory restricted comprehension down to this ordinary world where every function is Cartesian, and that included all the functions, and that you could talk about the universe of all the functions is only these Cartesian functions, as an example, Gödel also proved that there is an outside to that theory. Then to have an actual theory that's consistent and complete can still be a thing. You can call it the universe, the mathematical universe, it's a thing. And so researchers and foundations and historians of mathematics and mathematical logic will be interested in that. So then it says, so Henry John Stephen Smith, civilian professor of geometry at Oxford, wrote a paper, or Hankel did, on the integration of discontinuous functions. These functions do not really get in the way of the sensibility, fungibility, and tractability of integration, which is great. However, there's more. In 1881, Vito Volterra, who was pretty great, then a student at the Scuola Normale Superiore di Pisa, used a nowhere dense set of positive content, which he discovered independently as Smith, to construct a non-constant function f on 0, 1 such that f prime exists and is bounded at every point, but is not integrable. The meaning of such an example is that while f prime always has an integral in the sense of the prederivative, its antiderivative, it may not have an integral in Riemann's sense. It can then be said that Riemann's definition is beginning to show some rough edges, and there are more, because it was known, at least since 1875, that the equality, integral from a to b, of the limit as n goes to infinity of f sub n at x dx equals limit as n goes to infinity of the integral from a to b of f sub n at x dx need not hold. This is about the order of evaluation of limits and inside and outside, that they need not hold. And what that reflects on is the same thing to do with the scaffolding and the telescoping mentioned last time when I talked about tearing my hair out, about that the arithmetic of series could just be pairwise when it's an infinite series. That need not necessarily be true. And so here, when it's like this, so there are still conditions where it is so, and it affects symmetry and results and these kinds of things where they have a shared scaffolding, and what is the definitions of quantities hold up and out throughout all the thing. Here's a simple example due to René Louis Bayer. Define f sub n, it's from 0, 1 to R as follows: f sub n x equals 1 if x equals p over q, where p and q are integers with no common factors and q less than equal to n, and f sub n x equals 0 otherwise. So rationals and irrationals. And with q less than n. F sub n, like f sub 2, would be these, and these are called the Ferry sequences. A Ferry series, 1/2 and 1, 1/3, 2/3, and 1, 1/3, 3/3, and 1. That's another name for these, Farey. Each f, and so these fn's are those where q is less than or equal to n, and otherwise p, that the function is between 0 and 1, as that this function from the interval 0 or 1 is more or less to this set 0 or 1. It's just an indicator, this function. But it's on to R, and so what he says then is Baer says each f sub n is integrable because it is 0 except at a finite number of points. Oh, well, all right. But it's easy to see that the f sub n converges to the Dirichlet function, known not to be integrable. Not to be integrable. Well, I don't know about that, because usually people would say that if it's only defined as non-zero on the rationals, if that's a set of measures 0. And so these days you'd find people who would say that would be integrable. And so with regards to that being according to Riemann, I suppose then he's going to bring in Lebesgue and about the content 0 and content positive is its own thing. I had equated them to the measure positive and measure 0 respectively, but it's also limited to one dimension in terms of why it ends up being used as a construct that makes it so that these things that otherwise have any analytical character or content, that their content is non-zero, is the thing. What all this means is that the definition of integrability must come up for review, although this was far from clear in the 1880s. In view of Hankel's characterization of this concept in terms of sets of content 0, the first thing to do is learn how to measure the content of a set. Significant contributions in this direction were made in France by Marie-Anne Camille Jordan and Emile Felix Edouard Justin Borel, here for Jordan measure, but it was Henry Léon Lebesgue who, building on their efforts, was able to give a definition of integral superior to Riemann's. He accomplished this in his doctoral dissertation, Intégrale longueur R, written in 1902 at the Sorbonne, and later already a professor at the College of France, incorporated in his Leçons sur l'intégration et la recherche des fonctions primitives of 1904. And it says, a footnote says, C. T. Hawkins, Lebesgue's theory of integration, its origin and development, 1975. Lebesgue proceeded as follows. If S is a set of points contained in an interval A, B, and if the set I sub n is a sequence of open intervals in R such that S is contained in their union, then add the lengths of these intervals. Well, one might argue that, the open intervals, their lengths are missing the endpoints. Of course, these are considered removable, but add the lengths of those intervals. If this is done for all possible sequences of such intervals, the sums so obtained form a set of positive numbers whose infimum, that is the largest real number that is not larger than any of the sums, is called the outer measure of S. Its inner measure is defined to be B minus A minus the outer measure of A comma B minus S. Then A is said to be measurable when its outer and inner measures have the same value, and this value, denoted by M sub S, is called the measure of S. These days, the measurable is called giving it a sigma algebra, equipping it with a sigma algebra. Using Lebesgue's definition of measure, it is possible to show that 1, the measure of a set is non-negative, 2, a set is measurable if and only if its complement is measurable. Three, the empty set and any finite set are measurable and have measure 0. And 4, any interval is measurable and has its length as measure. These days it said if you can figure out a sigma algebra, it's measurable. 5 says if the set S sub i's is a possibly finite sequence of measurable sets, points in particular, then their union, the union of the S sub I is measurable with measure of union S sub I less than equal to sum of the measure of the S sub I, and equality holds if the S sub I are disjoint. And if S and T are measurable sets, then S minus T is measurable, and if in addition T is a subset of S, then the measure of S minus T equals measure of S minus N minus T. Because they're not disjoint when T is a subset of S. Then equals M measure S minus M is T, which implies that T is less than equal to M of S when T is a subset of S. So this goes back to the notions of union and intersection, that those are the properties that make it so that all this stuff for geometry is held up really easy and nice. Next, if S is a measurable set, the best define a function f from S into R to be measurable if and only if the set x and S, f of x greater than R, is measurable for any R in R. Turning now to integration, the basic idea, in order to properly account for any discontinuities of the function, was to partition its range into subintervals, not its domain. See, this is basically where, besides this apparatus, Riemann's got Riemann sums of widths that go to 0 by their heights, maintaining the proportion of the path elements or the line elements according to this Aristotle's continuum, or that the Riemann sums are like so and well defined according to how, from the intermediate value theorem and fundamental theorem of calculus, it's well defined. That Lebesgue just goes vertically with stripes instead of rectangles, vertical. Lebesgue's basic idea, in order to properly account for any discontinuities of the function, was to partition its range into subintervals, not its domain. So then it is kind of like that his discontinuities are it's not that different, but there's just both ways, so it kind of works out that one or the other way will have not a discontinuity. Was to partition its range into subintervals, not its domain. More specifically, let S be a measurable subset of A, B, let F, S to R be a measurable bounded function, and let M and big M be numbers such that M is less than Fx less than big M for every X in S. Then let M equals Y naught minus Y1 minus dot 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 minus Yn equals M be a partition of the interval M, which is like the Riemann, and the set S sub I equals X and S, Y I minus 1 less than F of X less than equal to Y sub I, represented by the union of these measurable areas that are disjoint, so there's some, in terms of paint, or how many cans of paint it takes to paint a unit square, by a brush that whose belly emits paint at a constant rate and only takes one coat. Represented by the union of the darkened intervals in the example of figure 2.11. Note that each S sub I is measurable because the sixth property of measure, since it's its own disjoint little region, and that these sets are disjoint, then it is easy to see that there's a unique number I such that the sum for I equals 1n of y sub I minus 1 and S sub I is less than equal to integral I less than equal to sum I equals 1n y sub I m S sub I. So that's as he puts it, for every partition M equals y naught da 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 y1 equals M of M big M. In fact, given epsilon greater than 0, let the partition be so fine that all the yi's are less than epsilon. All the differences in the yi's are this constant, monotone, strictly increasing infinitesimal differences for I equals 1 to n. Then the difference of the two sums above is the sum of the difference of the yi's by their measures, or you know, just like the vanishing thing, less than or equal to this epsilon, sum of, from I to n of the measures of the s sub i's, and that equals epsilon times the measure of the union of the s sub i's, which is less than or equal to epsilon times the measure of a comma b equals epsilon times b minus a, which approaches 0 as epsilon goes to 0. This unique number I is called the Lebesgue integral of f on s and is denoted by f of s, or the integral of f, or if s equals ab, by the integral ab of f. And so for the indefinite integral, it's written the integral with s, this sigma algebra of sorts, but not quite. Set of points that it's in the definite integral is written as f about the domain, and is in this set of points which has intervals and points and density and completeness and least upper bound property, like the reals or any other continuous domain which has a sigma algebra. Even a function as heavily discontinuous as a Dirichlet function, defined at the beginning of this section, is Lebesgue integrable. Oh, indeed, and I mentioned it would be 0. Indeed, if 0 equals y naught da 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 less than yn equals 1, is a partition of 0, 1, and each s sub I with 0 less than or equal to I less than n is empty, and s sub n consists of the rational numbers in 0, 1, which is shown to be countable by Cantor. Measure 0, countable sets of measure 0. Then the third and fifth properties of the measure imply that m of s sub I equals 0 for 0 less than or equal to I less than n on 0, 1, and that its integral is 0. It can also be shown that if a bounded function is Riemann integrable, then it is Lebesgue integrable. And that the two integrals have the same value. Well, I'm not so sure about that, because Hankel and Smith were just arguing the other way. That there's content. Then the third and fifth, it can be shown that the two integrals have the same value. Because, and then here, for example, that this checkerboard function must not be Riemann integrable. It's an outer integral of some sorts that has its own value. Thus, the class of Lebesgue integrable functions is larger than the class of Riemann integrable functions, of which it is a proper superset. I added that last part for the author. Furthermore, the Lebesgue integral is free from the defects. There's nothing good or bad about objects in mathematics. They just are. But when we ascribe things, words like defects to them, that means that what's otherwise sensible and fungible fails to be fungible, and so it becomes a pitfall or defect. It's defective. Furthermore, the Lebesgue integral is free from the defects of the Riemann integral that were pointed out above. First, if the f sub n is a sequence of measurable functions that are uniformly bounded, that if the absolute value of f sub n of x is less than big M on AB for some n greater than 0 and all n, this is the case with the functions in Baer's example, then formula 19 shows about exchanging the order of taking the limit on the inside and the integral on the outside. Baer's example of exchanging the order of limits is not necessarily sound. because of scaffolding and various concerns, but that it's not, it doesn't say much to just show one example. It's to explain where it does and does not hold. And this gets into all the laws of convergence, uniform convergence, and transit properties for an operator calculus of taking these combined operations in and out and considering them combined operations in terms of these quantities, as they've been being called here, derived quantities, and how they're derived. Furthermore, that is, the order of the operations of passage to the limit and interchange can be interchanged. About them being uniformly bounded. So here's making an example where for convergence that they can be interchanged. As an immediate application of this fact, Lebesgue showed that a bounded derivative, which need not be Riemann integrable, is always Lebesgue integrable. Indeed, if f is a function that has a bounded derivative f, we have the integral from a to x of f of s ds equals limit as h goes to 0 of 1 over h, integral from a to x of big F of x plus h minus f, big F of s plus h minus f of s. That quantity ds equals limit as h goes to 0 of 1 over h, bracket integral from x to x plus h of big F minus integral of a to a plus h of big F, kind of a intermediate value theorem, mean value theorem, equals fx minus fa. In this application, we have just a sample of the power of the Lebesgue integral. It should not be thought that its only virtue is to turn some pretty strange functions into integrable objects. That is actually neither here nor there. The point is that by allowing us to make very general statements, by eliminating any concern that a particular argument may be spoiled in the end by presence of one single function that is not comme il faut, fungible, comme il faut, the Lebesgue integral becomes a very powerful tool both for theoretical purposes and in applications. That's pretty great. And then he's going to get to, well, that gets to kind of the end of this section, this chapter. That he says, this is particularly so in the case of Fourier analysis in the field that Lebesgue chose to show the applicability of his new integral, and in particular of those new features that are not valid for the Riemann integral. He wrote several papers on the subject and even a book, Leçons sur les séries trigonométriques, in 1906. The previous year, Lebesgue had closed the full circle by giving a sufficient condition for the convergence of a Fourier series that contained all previously known sufficient conditions. Namely, we put g sub x of t equals this f of x plus t plus f of x minus t minus f of x plus minus f of x minus. Similarly, it's so as to how it's computed the average and mean and from the left and from the right. Then the Fourier series of f on negative pi to pi converges to the value 1/2 of this quantity f of x from the left minus plus x for f of x from the right. Another point x for which 1 over delta of the integral from 0 to delta of this absolute value gx of t dt goes to 0. As delta goes to 0 and the integral of from nu to pi of this absolute quantity gx of t minus gx of t plus nu over t, that dt goes to 0 as nu equals pi over n goes to 0. Then in his book, he closed a wider circle by showing that the Fourier series of an integrable function, convergent or divergent, can always be integrated term by term. It was this integration that allowed us to determine the Fourier coefficients at the start of this chapter. According to this formal apparatus, this provides a stack of sensible, fungible, and what to make what result tractable things to arrive at this stuff. There are others. There are other ways to formalize what makes so that the same kind of things, is the same kind of methods and means, and the results from sine and cosine being orthogonal, and the results from there being a weighting function, and the result from there being a Dirichlet kernel and a Feher kernel, and the results from there being the small angle approximation for sine, so that for any other pair of functions they can be interchanged and this kind of thing, make this kind of stuff so. But it's still a pretty great thing. There are others. They're all part of one great thing called the mathematical universe. All right, so the next chapter gets back into the heated bar, or the wire, the heated bar, or the heated wire, or slab. We'll talk about that at some other point. Because then that gets in, besides the Fourier series, then we'd talk about the Fourier transforms, or this maybe, or it gets in the differential equation about the Laplacian, and about that's the inverse square. And then it gets into about why there's trivial solutions like the zero solution. And then why does e to the x show up so often, and e to the x plus e to the negative x? What is that going to be about when x is large and x is small? And what about when it's 1 or 0, and positive and negative? And then there's other things to go on with about what are families of plane curves that are the kernels of, and maybe that's not the correct word to apply here, but are the kernels or bases or units of what results completions that make up for line elements in this way, that end up making integrable regions of about these what are points in these completions, their spaces that are individual of the continuum. So going back to the heap and Sorites paradox is like, well, if you have an infinity, when is it finite? The answer is never. You can take away stuff, eat one piece forever until it's gone, and then there's none left. But that never happens. And it's similarly from starting with 0 and counting upwards, the inductive impasse still exists between taking all the parts down to 0 or adding up all the pieces up to 1. So that's dealt with quite clearly here when it talks about the point set topology and the definitions and limit points, and still the properties that must arise and must only arise in what some Euclidean and what some continuous domain that's presumed to exist geometrically by an interval, and then how that works, that the definitions so arrive at they're maintained to exist either way, that then besides that there's the tremendous success, of course, of Newton's fluence and fluxions and Leibniz's differential, and how that survives to this day in both notation, form, and intent, although it's to be left out what are some of the algebraic uses of those, of the infinitesimal variables by an infinitesimal as quantities, because their derivations aren't scaffolded, but they still exist as things. That is, it helps to explain that what came up out of Cauchy and Weierstrass, of course, who weren't discussed so much, but they were basically the mathematics that was given to Riemann and is our formal apparatus for the real numbers, and then what arrived at that for Cantor then could then employ for his point set topology, but about set theory and the point sets, what happens when they're countable and uncountable, and what that means about Cartesian functions between them and the lack thereof, for the integers and the power set, the integers, and then as according to transitivity of sets having a cardinal and their membership in the same equivalence class equating to their cardinal, that then for Lebesgue and his working up of measure theory, and then using that for some of these functions which for Riemann became not fungible. They became not sensible because they left out a part of his formalism, the defect, not pas de comme il faut. That here, that's read with its just second grain of salt about how then what it results as for this, otherwise these considerations of these branches, the directions, that what was talked about includes things like, well, there's not uniqueness of the complete order field, because we have a non-standard continuous domain that's a prototype after Aristotle's continuum, and it has real analytical character and implements Jordan measure. And ditto for the Dirichlet function, there's a checkerboard function analog which is integrable and is not measure 0, but indeed has measure 1/2 compared to measure 1.0 for any interval of sufficiently large length. And then we getting into some of these things help explain what would go on. There's the course and the linear curriculum, which is if you follow it and stay on that track, it will hold up all these things. But then it gets into when you finally get up into like the mathematics of path integral, as was being read about here, and there's like line elements and path integral, and there's Jordan measure on the one side, which reflects this continuity, and then the Dirichlet function on the other side, and about how it's squeezed in or out, with regards to its measure and its analytical character. That those are what are the models that are left. And so then when it behooves one to know about the doubling spaces and the halving spaces, about these descriptive differential dynamics of the continuum dynamics, that's why it ends up being that it's so central in the theory of the mathematical objects, why this sort of continuum is so. Then, of course, that Euclid's geometry rises just fine on it. There's an origin everywhere. You're welcome to put a Cartesian basis and origin wherever you so care. It's fine. And then you can treat the whole thing in the local view as of an algebra in a group, including it being closed. Then you can think of all that as even that, as far as it goes, that's closed in terms of finite words and definable and undefinable and the countable and uncountable. You can still say for Goedel that's incomplete and thus open on the outside. Then it's sensible and fungible and tractable, the linear curriculum, while still being able to also even make a linear curriculum that doubles that and halves it. Makes one. All right, hey, well, have a great day.